Now let's take a look at the second derivative and concavity. Recall that the second derivative tells us if the change in the original function is occurring at an increasing or decreasing rate. Concavity describes the curvature of the graph. So let's consider these two graphs. Both the graph on the left and the right are increasing from A to B. But if we look at the graph on the left, function f, tangent line to every point is on the outside of the graph, and it is getting steeper and steeper. This means it is increasing at an increasing rate. And if you recall from section 2.3, it is increasing, which means our first derivative is positive or greater than 0. But because it is doing so at an increasing rate, we know that the second derivative will have the same sign, also positive. Now looking at the second graph, function g, the function is still increasing. And notice we take the tangent line on the outside of this function, the tangent line falls above, but the slope of those tangent lines start to decrease. They start off steep, but they get closer and closer to almost a horizontal line. This tells us function g is increasing at a decreasing rate. Again, the function is increasing, so we know that the first derivative is greater than 0. But since it's at a decreasing rate, the second function would have a different sign, so it would be less than 0. So how do these differ? First graph is concave up, which means the graph cups upward, like this. The second graph is concave down, which means the graph cups downward, like this. So how do we determine concavity? If second derivative is greater than 0 or positive for all x in an interval, then the function is concave up on that interval. If the second derivative is less than 0 or negative for all x in an interval, then the function is concave down on that interval. The point where a continuous graph changes concavity is called the inflection point. Now, the inflection point may occur where the second derivative is equal to 0. The second derivative must have different signs to the left and right in order for it to be an inflection point. So we'll have to check it. Now, these critical values of f prime are also called hypercritical values. Remember, we use first derivative for intervals of increase and decrease, and second derivative to find inflection points and concavity. So looking at this graph to the right, we can tell at the beginning, our graph is concave up, like a bowl. If it were to rain, it would hold some of the water. This means that our second derivative is positive. Later on in the graph, it becomes concave down, like an umbrella. Concave up, concave down. If you were to pour water on it, it would just roll off like a duck's back. That means over there, our second derivative is less than 0. So somewhere along that graph, it changes concavity. I'm not exactly sure where, but roughly there. It goes from concave up to concave down. This is our inflection point. This is where the second derivative equals 0. Remember, where it equals 0, it's not guaranteed to be an inflection point. We have to check and make sure that the second derivative changes signs to the left and the right of that value.